critical point of this function. Now, critical points are where both first partial derivatives are equal to 0. So that would happen when f sub x is equal to 0 and f sub y is equal to 0. Okay, so f sub x would be the derivative of this thing with respect to x. The derivative of 9 is 0. The derivative of negative 2x is negative 2. The derivative of 4y would be 0 because there's no x term in it. It doesn't vary with respect to x. The negative x squared would have a derivative of negative 2x, and negative 4y squared is going to have a derivative of 0. Okay? We need that thing to equal 0 to get a possible critical point. Now we need to find f sub y. So if y is the variable, the first two terms have a derivative of 0. The 4y has a derivative of 4. The negative x squared term, this has a derivative of 0. And then the last term has a derivative of negative 8y. So we need that to equal 0 also. So what you notice is, compared to the last time we looked at finding critical points, we don't have a system of equations, do we? Right? The first equation is just saying, hey, x needs to be 1. If x is 1, then that partial derivative will be 0. The second equation is that y needs to be a half. Because if you did 4 minus 8, or 4 minus a half of 8, you'd get 0. So that equation is just telling us that y is equal to 1/2. So if we want both of these things to happen simultaneously, then our critical point is just 1 comma 1/2. Because if x is 1, the partial derivative with respect to x would be 0. If y is 1/2, the partial derivative with respect to y would be 0. So that's a critical point, which implies, thank you, I better be careful here, right? This should be negative 1. All right, good. And this is negative 1. So that said, the same reasoning holds true. This needs to happen to have the partial derivative with respect to x to be 0. That needs to happen with the partial derivative of y with respect to be 0. So that's the single place where we can go. We'll be guaranteed to have a horizontal tangent plane. Okay, so the question now is, how do we look at this point and decide if it's a max or a min? That's what we're going to do today. Okay, and it turns out you need something called the second derivative test for a two-variable function. Now, before I introduce you to that, let me just remind you of something you learned a while ago back in the 2D world. So back in the 2D world, here was what you would usually do. You'd look for candidates. You'd look for critical points, and you'd say, you'd want to know where they were. So you'd have a function. You'd find a place maybe where, here's a place right here where the derivative was equal to 0. You'd say f prime of x equals 0 here. Let's call this a. So f prime of a is equal to 0. And you had two ways of testing if this thing was a max or a min, right? One way was to look at the slopes on either side. So you'll notice that the slopes over here to the left of this critical point are negative. And since the slopes are negative, it means we're decreasing here towards this point. And then after that point, we see that the slopes are all positive. Right? We could write that this way. F prime was greater than 0 here. F prime was less than 0 here. And that meant the function was increasing over here. And if you went from decreasing through a slope of 0 to increasing, then we said, hey, the function had a minimum there. So that was the popular way to decide if a thing was a max or a min. But there was a second way. And the second way was to do something called the second derivative test. In other words, what can we say about f double prime of a? Right? F double prime measures concavity. It's talking about whether the function bends upwards like this. If it's concave up, then it looks like that somehow. And if it's concave down, then it looks like that somehow. Right? So what can we say? Well, this function, if you look at it near x equals a, it sure looks like this case up here. So we could say that f double prime of a is greater than 0, or the function's concave up. Well, if you have a function that's concave up, and then at a particular point where it's concave up, the slope's equal to 0, then it has to be a min. So that's the second derivative test for a single variable function to decide if something's a max or a min. So the last thing I'll say about this is notice that in the case where a function is concave up and you have a minimum, that the tangent line you get lies completely below the curve, near the point of tangency. Okay? And if you give that a little bit of thought, that sort of sort of convince yourself that that always happens. Here, just draw a smiling parabola. Well, we know this thing is always concave up. If you draw any of its tangent lines, pick any point on here and draw a tangent line, what you'll notice is that tangent line lies below the parabola near the point of tangency. Okay? And that's actually what the goal is of the second derivative test in the two-variable world, is to sort of decide, we found the place now where the tangent plane's horizontal. We know the tangent plane's horizontal when x is equal to -1 and y is equal to 1/2. So the question is, how do we find out if the following is happening? So here are some cases. Suppose we talked about the paraboloid before. So here it is, the paraboloid. And if we looked at the tangent plane right here, that tangent plane lies below the paraboloid and all the points nearby. So that allows us to conclude that there's a min here. So turn the paraboloid upside down now, and you end up with this. And here's the high point, and if we draw that tangent plane, that blue tangent plane lies completely above the paraboloid near the top of this hill. Okay? So this is a max. Okay? Now, these are not the only things that can happen. Let me go back to the 2D world for a minute, because there were examples of functions in the 2D world where you didn't luck out. You'd find a critical point, but there wouldn't be a max or a min. So the famous example of this is y equals x cubed. So y equals x cubed has this weird phenomenon. When you look at the tangent line at the origin, it's horizontal, but the tangent line on one side is below the curve, and the other side is above the curve, and therefore it's not a max or a min. Okay? Well, there's something analogous to that in the 3D world. What it ends up looking like, usually it's called a saddle point. So you can have a parabola in this direction and a different parabola in that direction. So you can have this thing, it ends up looking like a saddle. When you draw the tangent line here, the tangent plane that is, parts of this surface are above it and parts of it are below. And therefore, this is not a max or a min. Usually we call it a saddle point. Literally because it looks like a saddle of a horse that you would sit on. Okay, so how do you do the second derivative test? I mean, in the 2D world, it was easy. We just computed the second derivative. We plugged in a number. If it was greater than 0, the function was concave up, and we knew it was a min. If the second derivative was less than 0, we knew it was concave down, and the function had a max. But it's a little more complicated than that in the 3D world. So here it is. So earlier we found out that the critical point of this function was -1, 1/2. What we'll do is try and apply this second derivative test. Now let's remind ourselves, A stands for the second partial derivative with respect to x at the point, the way it's written here, x0, y0. Capital B stands for f of xy at the point x0, y0. And capital C stands for fyy at x0, y0. Okay, so we know we're interested in, if you look at second derivative tests, you know you're interested in computing this expression. So we're going to find that first and see which category we fall into. Okay? So let's go and do that. So A is going to be the second partial derivative with respect to x. Now let's remember what the first ones were. F sub x equaled -2 minus 2x, and f sub y equaled 4 minus 8y. So A is going to be the derivative of that thing with respect to x, but that would just be -2. B would be the derivative of this thing with respect to y, but that would be 0. And then C would be the derivative of that thing with respect to y, but that's -8. Well, you'll notice that the way this thing is written, we're supposed to take the critical point and sub it into each of the second partial derivatives. But we don't need to do that here because there's no variable in there. So we can immediately compute the thing that we're interested in, this expression, AC minus B squared. That's what we really want to know about. So AC minus B squared in our case would be negative 2 times 8, or 16 minus 0, or 16. So here's what we know. We know that AC minus B squared is greater than 0, and we know that A is less than 0, and so is C. C is less than 0. So let's go find out what case we're in. So we go up here. We're in one of the first two cases, but we're in the second of the two because A and C are both less than 0. So here we are, and that means that this thing has a maximum point at negative 1, 1/2.